Hi. So, I want to welcome you to the final video from this class. So, this is the last thing you need to know, and we're going to do an illustrative example on Solow Growth. So, basically what we're going to do is we're going to use Cobb-Douglas production function to actually find steady state level of capital per effective work. Okay, so let's just say that the production function we are dealing with is Q equals to K alpha times A L to the power y minus alpha. Look, in this case, we can easily demonstrate that we have constant returns to scale, right? Because the sum of those two is simply 1, but let's just demonstrate it. Okay, so look, if instead of capital we would have A times capital, and instead of effective labor we would have A times effective labor, we can take A over here and over here out of the parentheses, so we would have A to the power of alpha times A to the power of alpha, 1 minus alpha times K to the power of alpha times AL to the power 1 minus alpha. This gives us, of course, A and of course this expression that you see, over here and over here is equal to Q. Okay, so we know that this function exhibits constant returns to scale. We've done it very many times before. We proved that this function actually exhibits diminishing returns to factors. So from this moment on, let's just focus on the derivation of that model. Okay, so look, if this is the production function we are dealing with, we can make a couple of very simple tricks. A couple of very simple tricks with this function and transform it to the form it would be more suitable for us. Well, the trick that we've used in the general form was to take AL out. So, if we're gonna take AL out, look, those two add up to 1. So, if I'm taking AL out, what I'm getting as a result is K over AL to the power of alpha times AL over AL to the power of 1 minus alpha. Now, going further with this, we get that this is just 1 to the power 1 minus alpha. So again, it is completely unnecessary because this will always be equal to 1. So we get that this is AL times K to the over AL to the power of alpha. And now look, let's just simply define capital per effective worker just as we did before. So lowercase k is equal to K over AL, and we get that this is simply AL times K to the power of alpha. Okay, and look, again, if we just look look at the two expressions at the very ends, we get that level of production, so Q, is given by A, L, times K to the power of alpha. And from this, we get that production per effective worker is given by K to the power of alpha. Okay, so look, this is a specific form of the general production function we were using previously. Because look, when we were deriving the equation of motion or the law of motion in the Solow Growth model, we've ended up with this. That's K with the dot. So derivative with respect to time of capital per effective worker is equal to S of K minus minus rho plus lambda plus delta times K. And look, what we are going to do now is we're going to replace this general function with the specific function we've assumed over here. So, as a result, we are getting that change in capital per effective worker is equal to S times K to the power of alpha minus rho plus lambda plus delta times K. Okay, so I hope at this moment you're starting to see that this is a differential equation, but this differential equation has a specific form, which means probably we might be able to solve it. But of course, this looks not like a linear differential equation that linear differential equations we're dealing with do far. But look, let me just make one simple change over here. Because look, if I'm gonna just simply move this to the other hand side of the equation, what am I gonna get? Okay, have we seen this somewhere? Okay, let's just say that instead of K, we would have dy dt. Now, instead of this, we would have R. Then, of course, instead of K, we have Y, right? K with a dot, right? Is derivative of K with respect to time. Then T times Y to the power of M. So, what we see over here is again a case of Bernoulli equation. The good thing about Bernoulli equation is that we know very well how to solve it. Look, the only difference between the two is that, of course, here instead of dy dt we have dk dt, which we can simply write as that, and y needs to be replaced with k. Okay, so what do we have in this case? We've got that our r is equal to rho plus lambda plus delta. T is equal to just S, lowercase s, the savings rate. Our M is equal to alpha and alpha is somewhere between 0 and 1, so it's neither 0, neither 1. So again, everything here is the way it should be, right? So what do we do when we try to solve a Bernoulli equation? Well, we perform linearization, right? So we need to define variable z, and this variable z is going to be equal to a k to the power 1 minus m, which in our case, this is k to the power 1 minus alpha. Okay, the next thing is simply to use the formula for a linearization. So we get that then that we've got dz plus 1 minus m times r z minus 1 minus m t dt equals to 0. Right? So let's now substitute all that we've got over here. So we got dz plus 1 minus alpha times rho plus lambda plus delta z minus 1 minus alpha s dt equals to 0. Okay, so now the best way to proceed is to divide both sides by dt. So we've got dz dt plus 1 minus alpha rho plus lambda plus delta z. And look, what I'm going to do right away as well is to move this expression to the other hand side of the equation. So I'm going to have here 1 minus alpha s, and that's it. Okay, so look, what do we have over here again? This is a linear differential equation with constant coefficient, constant term. So not a problem over here. Look, this is simply our A. This is our B, right? So equilibrium value of z in this case. So particular integral in this case is simply b over a, with a and b over here. So look, we would have that this is 1 minus alpha s over 1 minus alpha times rho plus lambda plus delta. Those two cancel each other out. So we end up with very elegant solution, rho plus lambda plus delta. Okay, so knowing this, we can substitute this to the complete solution, and the complete solution would be, right? First, we need to have deviation from equilibrium. So z0 minus zp, right? So our equilibrium Then, what else we need to have now? Well, we need to have e to the power negative a, right? This is our a. Now, a is a little bit long here, but we can manage. Is 1 minus alpha and times rho plus delta, plus lambda plus delta, times t. And finally, plus the solution, so we've got particular integral s over rho plus lambda plus delta. Okay, so now look, we've got a solution, but this is a solution for z. Of course, remember, we need to know the solution. We need to know the solution for. We need to know the solution for. We need to know the solution for k. But I hope that you remember that we already defined this over here, so it shouldn't be that much of a problem. Okay, so let me erase this. We don't need anything from here anymore. Okay, and so we remember that z of t is equal to k of t to the power 1 minus alpha. So we get that k of t to the power 1 minus alpha is equal to k0 minus s over rho minus plus lambda plus plus delta times e to the power 1 minus alpha rho plus lambda plus delta times t plus s over rho plus lambda plus s. Okay, and look, now we can very easily calculate whether the convergence takes place over here. All we need to do is to calculate limit with t approaching infinity out of k of t to the power 1 minus lambda. And look, we know that alpha is always between 0 and 1. This is a standard assumption with Cobb-Douglas production function and constant returns to scale. So this expression, of course, is positive. Now, growth rate of technological progress, population growth, and depreciation, they are both positive expressions, so their sum also needs to be positive. Finally, and I can just find another color, the minus here that we've got at the beginning makes this entire expression negative, which leads us to the conclusion that as time progresses, this expression gets smaller and smaller and smaller, and as time goes to infinity, it just goes to 0. Which shows us that the limit with t approaching infinity out of k of t to the power 1 minus alpha is simply our particular integral. So this is s over rho plus lambda plus, oh my god, so this is the worst delta ever, and plus delta. Okay, and look, so we are almost ready to get the steady state level of capital. What would it be? Well, look, we just need to solve this very simple equation for k. We got that z is equal to k to the power 1 minus alpha. So if I want to solve it for k, what do I need to do? Well, I need to take both sides of this equation to the power 1 over 1 minus alpha, right? When we we take to the power both sides, we multiply the exponent. So we get from that this would be 1, and we got that this is z to the power 1 over 1 minus alpha. And finally, using this result, instead of instead of z, we get that steady state level of capital in this economy is given by S over rho plus lambda plus delta to the power 1 over 1 minus alpha. And this is the final solution. So, as you see, once we know how to solve, how to use Bernoulli equation, finding a steady state level of capital in the Solow Growth model is really easy. And look, from that we can easily get what is the level of output. How can we do it? Look, all we would have to do is to substitute this result into the production function, which I will leave for you as an exercise that you're probably going to do with Valeria during the workshops. So look, this is it. This is everything you need to know for this class. And very shortly, I will explain to you what is going to be on the final exam. Thank you for your attention and good luck on the exam.